All right, let's take some time to talk a bit about the efficiency of an algorithm. When we talk about efficiency, usually in this class, what we'll be talking about is the idea of time. How much time does it take for an algorithm to actually run? There are other types of efficiencies that we can measure. Another common one would be space efficiency. So, how much space does an algorithm require, or how much memory does the algorithm require? This one is sometimes talked about, and we will talk about it in some cases where it's relevant, or in some cases where it's the main differentiator between algorithms. But primarily, we'll focus on time, since time is the main resource that we don't really have a way to work around, right? We can throw more hardware at space, we can't throw more hardware at time. So that's primarily where we're going to focus for most of this course. Now, when we take a look at the idea of time, you may at first say, well, that seems like a pretty easy thing to do, right? I've got an example function here, and you could say, well, we can measure the time of this, right? For instance, I could import the timeit library, and then basically what I could do is I could just set up a timer. So I could say t equals timeit.timer, and I could do a timer that is going to actually run my function. So we just do a lambda of the example. I give it in any sort of list of values, and what it will do is it will sum up this list of values. And I can say how many times to run it once I actually print it. So we'll print out t.timeit, and I will run this function, say, 1,000 times. And what it will do is it will average the amount of time it takes over 1,000 runs, and we'll get our results. So if I do a Python 3 of this particular file here, we'll do, it should be lowercase linear search. There we go. We'll see it takes like not even close to a second, right? 0.0001 of a second. And you see that as we run this, the time actually varies a little bit. And what I would do is I would encourage you to try running this on your computer. And what you'll find is, unless you're on the same hardware as me, running the exact same setup, your times may vary from mine. And you'll see this a bit more clearly as you increase this number, right? So as you increase this, the amount of time is going to increase as well. Once you get into like the larger sort of time periods, you'll see a bit more fluctuation, right? Now, this sort of fluctuation is really interesting. And it turns out that this sort of measure doesn't work too well for us. And the main core reason is that it's going to differ based on the computer that's run on, right? The hardware is going to change things. The programming language is going to change things. That means the implementation will generally change things. So overall, it's not going to be a great measure of the amount of time an algorithm takes. We want to have a more general measure of the actual time. The other thing that's really interesting about this is that actually as this array increases in size, right? As I increase this in size, you'll find that the time actually increases as well, ever so slightly, but it does increase, right? And as I make this bigger and bigger, the amount of time is going to increase proportionally. So we have a few problems here. So the main problems is, how do we measure time in a more objective way? I don't want to have it relying on hardware. I don't want it to rely on implementation. So I want it to be very general. The second thing that I have is, how do I actually measure the time respective to the input size? So I want to be able to say, as the input size increases, what happens to the amount of time required to run my algorithm, right? So we go back to the drawing board and we say, okay, what can we do here? One other idea that we could consider is operations. An algorithm requires a number of operations to actually execute. The number of operations, generally, we're going to have a set of operations that will run in a constant amount of time, right? So there's certain operations in here that are going to run in a consistent amount of time every single time that they're run. So for instance, setting sum to 0 would be storing data in memory. That will be constant time. No matter what I'm storing in memory, generally it takes the same amount of time to run, right? So it's just like generally one CPU instruction to do that. Similarly, this sum operation may just be basically one operation. It's going to just add the sum and x together. So, that will take a consistent amount of time to actually do. What we could do is we could say, what if I count up all the different operations that are in my function? And that would give me the number of operations that existed. And then basically what I could say is, on a computer, we could just figure out how long an operation takes on that computer. We multiply it by the number of operations. That tells us the amount of time that the algorithm actually takes. Well, that seems like a pretty good approach, so let's give it a try, right? So to take a look at this, I've got one operation here, and then I've got inside of this loop, we would say that this is, we could sort of say that it's one operation or two operations, right? Basically what will happen is it will retrieve the value of sum, and it will add it to x and then store it back in sum. So I'm going to say it's three operations because it has to retrieve the value, it has to add the value together, and then store it back in its place. So we'll say that seems like three operations, and then maybe this one here seems like one operation as well, right? And what happens is these three operations repeat for everything inside of the list, right? So we have to account for that. So how big is the list? Well, the list could be any size. So what we would do is we would say the length of the list, we're going to represent as the variable n. So we're going to say n is equal to the length of the list. Therefore, when this loop runs, it runs this operation there's three operations, right? N times. So that means that it would be 3 n operations, right? So overall, when this runs, it would require 3n plus 2 operations. So these two operations run one time. This one runs 3n times, right? And you can represent this as a function. We could say f of n is equal to 3n plus 2, where n is the size of the list. You could plug in any n value here. It gives you the number of operations that are required. And like I said, if you know how many operations are, or how long an operation takes on a computer, you can multiply that out and figure out the amount of time the algorithm takes. This seems like a pretty reasonable approach, right? So this seems pretty solid. Are there any problems with this? Well, there's a few problems. The first problem you saw when I was talking about this operation here, I said it looks like it's about 3 operations, but the number of operations that this actually requires will vary, right? Depending on the CPU, we may have different sets of instructions. So the idea of what counts as an operation becomes a bit tricky, right? It kind of varies a bit based on the hardware still. So that's a bit of a problem. The other, much more major problem for us is implementation. What if I had decided to implement this algorithm like this? I could say sum equals 0, and then what I could do is I could create a while loop. I could say I equals 0, and I could say while I is less than the length of L, and then I could do sum plus equals L at I, and then we could do I plus equals 1, and then we could return the sum. If I did things this way, well, things change a little, right? Let's zoom this out a little bit so we can maybe see both of these as much as possible. Well, we got one operation here, we got one operation here, right? Inside of here now, we still have this same 3 operations, but we also have this operation happening, which technically is a retrieval and an add and a storage as well. So we could call this 3 operations, and then we could call this 1 operation, and then, well, suddenly things have changed. For this implementation, suddenly this is taking 6n plus 3 operations, right? Do you see how just by changing this from a while loop to a for loop, the number of operations has changed, right? But it's the same algorithm, right? So this is a bit of a problem for us as well. This is dependent on the implementation. It turns out that what I really care about is I care about how the operations are changing as the input size changes. So generally, as the input size increases, what happens to the number of operations? And to understand that rate of growth, what I really need to focus in on is the highest order term in this number of operations. So all I actually really care about here is this n, right? This n tells me that what's happening is as the input size grows bigger, the actual amount of time it takes is also growing linearly because the number of operations grows linearly, therefore the amount of time also grows linearly, right? So that tells me a lot more clearly what's actually happening. So this is actually the way that we're going to analyze these algorithms. We're going to say, you know what? We don't really care about the constants. They're not really important. All we really care about is the highest growth term. We actually refer to this as something really special. It's called asymptotic notation. What asymptotic notation does is it says, as n grows really, really large, what happens to the amount of time the algorithm actually takes? So as n grows really, really large, what happens to the growth of this function here? That's what asymptotic notation is looking at. And what you'll find is that there's actually a few different kinds of asymptotic notation. We'll get into the details of that a little bit later. We'll get into those more technical details to understand that. But generally what we could say here is that we don't really care about the constants. We just care about the growth. How does the actual algorithm time change based on the actual input itself? So that's the general idea of what I want to get across. Before I finish up here, let's just take a look at another example of this actual problem. So let me write out another function here, and we'll take a look at another example to see just how this is generally working. So suppose that instead of having just one list, or well, we'll leave it as just one list, and what we'll do is we'll just say inside of here we'll have another loop of L for some reason, and then inside of this we'll do this equals x plus y. Okay? So we just change around the algorithm a little bit. but there's a few major changes that we have to account for here. Inside of this loop, we still have a number of operations. And like I said before, I don't actually care about the constant. I'm going to drop it. I'm just going to care about the main term that's happening here. So the main term that's happening here is that we have an operation that's happening, and it's happening n times in this loop, right? Where n is the size of the list L. Now this outer loop also repeats. So each time that this loop repeats, everything in here repeats. This loop repeats n times. This also repeats n times. So I actually end up with n times n, right? Which would be n squared. So generally this requires around approximately n squared operations to complete. It's technically like n squared plus 2, and there were some constants inside of there, but we're going to drop all those and just say the rate of growth is n squared. As the input size increases, the actual amount of time required, or operations required, also increases quadratically. So not linearly in this case, quadratically. And then we could ask the question, which of those is better? If something grows based on quadratic, and one thing grows linearly, which one is better? Well, the one that grows linearly grows slower than the quadratic one, right? So that tells us that if we had a choice between those two, we should pick the one that grows linearly because that one grows slower. As the input size grows, it has less operations generally than the quadratic one. The quadratic one will always end up with more operations after a certain point, right? So after maybe a specific point on the graph, eventually n squared will always be bigger than n, right? So that gives you some of the basic ideas around how we're analyzing the time of algorithms. In the next video, I'm going to dive more into the actual idea of asymptotic notation. It will discuss the theoretical aspects of what asymptotic notation really is. I'm going to break down the actual mathematical theory behind it. It's going to be a fairly rigorous video, so if you're really just looking to understand algorithms at a high level, it's not necessarily required to go through that, but I want to include it here for anyone who's interested in understanding why we can actually drop the constants and what that really means for our analysis. Also, don't worry if the idea of analyzing these algorithms feels a little bit complicated to start. We're going to be doing this literally every algorithm, so you're going to see this so many times. By the end of it, it's going to be completely natural to do an analysis on these algorithms. So this gives you a high-level idea of what we're looking at with time complexity. Thanks so much for watching. I'll see you in the next video.